We are looking at the beginning of differentiation, where you might have calculated an estimate for the gradient of a tangent. And so what you're going to do in this video is, beyond that a little bit, we're going to use the power law to expand or simplify polynomial functions so that they're easier to differentiate. So let's look at this. We have dy over dx, which is the derived function, and we're going to use that power law from the right hand side. So we bring our exponent of 3 out front, and we multiply that in a moment, and we take away 1. So you do that over and over basically. However, we have to rearrange some parts. So we may have to rearrange a part in a moment. Any constant, so root 13 or any number on its own is a constant. You can basically bring that to 0, because let's say it was 2. 2x to the power of 0, you would have 0 times 2, which is 0. So we've solved that there. You'll just multiply those parts out yourself and you'd see it gets simplified. The second one here, we have a fraction for our exponent, so be careful here. So we multiply it and then take away from 1. So 1/3 minus 1. Minus 6 times minus 1/3 x minus, so exponent of minus 1/3 minus 1 again. So 9 over 3 is 3. And take away your exponents there as well. So we're simplifying, perhaps expanding now and then to make these easier. And of course, when we get this, if you were given a point, like an x value, you could plug in that value and you would find the gradient at that point. And that's why we use this. We will now look at some polynomial functions, being simplified and expanded again, but using the chain rule as well. So an extra technique here. So basically your dy over dx, you can also kind of look at it as connected rates. So you have dy over du times du over dx. And we'll see what that means in a moment. So you see the first question, we've got 1 over x. You need to rearrange that. So simplifying, rearrange it as x to the minus 1. And that's the inside part. So u is our inside the brackets part. We find a derivative for that. So we'll differentiate that. You end up with what we have there. Secondly, we have y equals, so the whole thing itself, we'll call that u to the power of 4, which is the outside part, 4. We'll also derive that, or find the differentiated function of that, which is 4u to the power of 3. Now we can start to put it together. So 4u to the power of 3 times, I'm going to just move that around, so it's 2 minus x to the minus 2, and then plug in your u again. And I'm going to just rearrange that again as it was in the original question. So it's the power of 3, yeah. And then it's like an extra part being put in here. So there's a sense, you're adding a link here, and you just want to practice so many these kind of questions, some of them just see how it works. It's a composite function. So the rule is that you have those two parts. So for the second one, we'll do the same. And the rearrangement will definitely show how the polynomials work as well, because we need to express them in a certain way, with the powers especially, with the exponents. And again, we'll have dy over du, which is minus 2u to the minus 3 times du over dx. And we just put it all together. And remember the last part here, we're going to reinsert what we substituted for u. So minus 2 times 3 is minus 6. Put in our inside part, and then have that last part at the end. So it's times x squared there at the end. Now I want to simplify it again, just to put it as it was in the actual question. So let's just say, if it's minus 3 as the exponent, you want to put that underneath as a denominator. So that's the start of differentiation. And you're going to have more questions that will have roots. So just remember, like, the root of x is x to the power of a half, and so on. And you'll also have rational functions. So just rearrange them with the exponent. So if it's 1 over x to the power of 4, it would be x to the power of minus 4. You can rewrite it like that. So just keep that in mind when you're doing some of the simpler polynomial questions.